Welcome back. We are doing some problems. In the previous session, we exhibited polynomials whose Galois group is S5 or more generally SP, where P is a prime number, and thereby we showed that these polynomials cannot be solved by radicals. Okay, so and these solutions required a little bit of work which I did not conclusively prove, but these are left to you to explicitly construct show that the polynomials we constructed will have only 3 real roots and 2 non-real roots. So that is an easy exercise that you can do. So now let's continue with the second problem. So the first problem was to do SP, and we looked at some interesting examples of that. But let's now do compute Galois groups of some polynomials. Okay, so I'm going to go a little fast with these examples. I'll indicate what needs to be done and maybe leave some exercises for you to do along the way. So let's do some simple things first. I mean, for example, x square plus 1. So I'll simply write the Galois group is here z mod 2z, and if you take x square minus 1, the Galois group is trivial. So if you take a degree 2 polynomial, its splitting field will have Galois group as subgroup of S2. So if the polynomial is irreducible, it will be all of S2, which is z mod 2z. If it's not irreducible, then it will be trivial. So I just want to settle that simple case first. Now let's look at cubics. So that is degree 3. Okay, so we know that, and we assume that f is irreducible. Otherwise, it will be a product of linear and degree 2, which we have already considered. So there is no reason to look at it again. So we assume f is irreducible. Then Galois group of f is either A3 if discriminant of f is a square in f, wherever your f is defined. So if the base field is f, then if it's square, it is a, and if the discriminant is not a square, so this is just to recall what we have done. Okay, it's not a square, that means it's S3, all of S3. Okay, so a useful formula that can be proved using some tedious computation is the following. If you take a polynomial, a irreducible polynomial of if you take a degree 3 polynomial without any degree 2 term, something like this, where a and b are rational numbers, let's say, the discriminant is actually minus 4a cubed minus 27b square. Okay, this is an exercise. I have written down the discriminant for an arbitrary degree 3 polynomial earlier in the course, but if you apply that with the quadratic term being 0, you get this. Okay, so just using this, let me just give you 2 examples. So if you take x cubed minus x minus 1 in qx, okay, so check that it is irreducible. I am going to give you a quick reason why in a minute, but it is irreducible, one can check. Then what is the discriminant? This is equal to, this is a polynomial of this form, right? It's called a depressed cubic, meaning x square term is not there. So a is minus 1, so minus 1 cubed is minus 1, so that is 4. B is minus 1, b square is 1, so this is minus 23, not a square, so the Galois group is S3. Okay. On the other hand, if you take x cubed minus 3x plus 1, again check that it is irreducible. Then discriminant is minus 4 times minus 3 whole cubed, that is minus 27. It will be plus 27 because minus 27 minus 4 minus 27 b square. So that is, sorry, this is minus, but then it will be 4 times 27 minus 27. B is 1, so that is minus 27. So this is 3 times 27, which is of course 9 square. So this implies Galois group is A3. It is a cyclic group of order 3. In this case, it is S3. Okay, so I wanted to do these two examples because I wanted to indicate that both cases occur. So this is not particularly surprising to you. We have discussed these such things in the past. Okay, so just to give you one test for irreducibility, which maybe I have not discussed earlier in the course. In the beginning, when I gave you some irreducibility tests, I don't recall if I did this. So usual things are Eisenstein reduction modulo P, but this is also very useful. So this is, if f is any arbitrary polynomial like this with integer coefficients, and of course we assume an is non-zero, but we will also assume that an times a0 is non-zero. So both the leading term and the constant term are non-zero. Leading coefficient and constant coefficient are non-zero. So then let us take two integers r and s which are co-prime. Okay, so co-prime. Then r by s is a root of f. So rational root test tells whether r by s, a given rational number, is a root or not. It at least says when it cannot be a root. Then r divides a0 and s divides an. Okay, so this is easy proof. So a general version of this is from Eisenstein criterion, but you can, or Gauss lemma, but you can directly do this because if you do, this is standard. So if r by s is a root, you have a by an times a1 r by s plus a0 is 0. So this implies an r n plus an minus 1 r n minus 1 s. You multiply by Sn, I mean. So then you get so you get a1 r Sn minus 1 plus a0 Sn equal to 0. So multiply by clear denominator, I mean. So you get this. But this implies, so I'm just quickly giving you a reason for this. So by taking the last term on the other side, you get r times an rn minus 1 plus a1 Sn minus 1 equals minus a0 Sn. So all the terms except the last one are divisible by r. So this implies r divides a0 Sn, but a0 r and s are co-prime, so r divides a0. Okay, so that is the first part. Similarly, you can get s divides an. So this is very useful, especially when you have leading term 1 or constant term 1, like in these examples. So all you need to check is that here these are degree 3, so they are irreducible if they have no roots. So any root must have, right, because constant term is 1, leading coefficient is 1. So only possible rational roots are 1 and minus 1, which you can quickly check are not roots. Okay, 1 and minus 1 are not roots for this. So these two cubic polynomials do not have roots, so they must be irreducible. Okay, so this rational root test is a very nice, convenient way of checking irreducibility of degree 2 or degree 3 polynomials. Okay, now let's go to the quartic case. And again I am going to take an irreducible quartic, because if it is reducible, its roots are already in, it's already a product of smaller degree polynomials whose Galois groups we have discussed. So there is no new phenomenon. All you need to do is consider irreducible quartics. So I want to introduce certain new So then first I want to do some simple ones before I give you some general formulas which help us. If you take x power 4 minus 2 as your f, its roots are, as we know very well, the roots are plus minus 4th root of 2 and plus minus I times 4th root of 2. So 4th root of 2 is a real 4th root of 2. So you take plus minus 4th root of 2 and plus minus I times fourth root of 2, because I is a primitive fourth root of unity. Every time you have a real fourth root of 2, you can multiply by I to get other roots. Okay, so let's say alpha 1 is fourth root of 2. So I want to just explore what happens here, recall the analysis that we have done for quartics. There we had to first consider resolvent cubic. Resolvent cubic was x minus beta 1, x minus beta 2, x minus beta 3, where beta 1 is alpha 1 alpha 2 plus alpha 3 alpha 4 and so on, right? So in this case beta 1 will happen to be, so if you call them alpha 1 alpha 2, actually yeah, so alpha 1 is this, alpha 2 is I alpha, alpha 3 is minus alpha, alpha 4 is minus alpha 2. So this is how I define label the indices. So there are 4 roots like this. So then beta 1 will be actually alpha 1 alpha 2, which will be I times alpha square. So alpha is equal to alpha 2 plus alpha 3 alpha 4. So that's also alpha 1 alpha 2, which is also alpha I times alpha square. So 2I alpha square, which is of course 2I root 2. If you do beta 2, which is alpha 1 alpha 3 plus alpha 2 alpha 4, you see that it is 0. Okay, so that is a simple calculation, and beta 3 is minus 2I root 2. So I don't want to spend too much time on this. This is just a computation which is not that interesting, so I will breeze past this. But then we can now compute G, that will be x minus 2I root 2, x plus 2I root 2 times x. X minus beta 2 is 0, x. So this actually will give you x times x square plus 8, because 2I root 2 whole square is 4 times minus 1 times 2. So this is x cubed plus 8x, and this is reducible. In fact, has exactly one root in cube, right? So if you now recall the table for so G reducible, G irreducible, D square, D not a square. So right, these are the 4 possibilities. I think this was A4, this was S4, this is D2, this is D4 or C4. So G is reducible here, and even without looking at the discriminant, we know that the Galois group of F must be D2 or D4 or C4, because this case cannot occur because G is reducible. And I think we in fact analyzed it further. If it's completely reducible, then it is D2. If it has exactly one root, it's D4 or C4. Okay, so we can rule this out, right, because G is not completely reducible in Q. But which one will occur here? So now here is where we look at the degree. What is the degree of K colon Q? K is of course the splitting field. So K is nothing but I and 4th root of 2. So this will have degree 8. It is 8. Right? Now only D4 has order 8, C4 has order 4. So this cannot happen. So looking at the specific polynomial, we conclude that it is D4. Okay, so let me just give you some more simple. Okay, so I hope this is clear. So here it is D4, and this is in fact something that is not new for us. We have considered this. So if you do x4 plus 1, here the roots are plus minus 1 plus minus I. Okay, so you can actually by hand compute the resolvent cubic. G will always denote resolvent cubic for me in this situation. Resolvent cubic is actually nothing but x cubed minus 4x. Okay, so this is an exercise. So you take all the beta i's and you compute this. So this completely reduces, completely splits in Q because its roots are 0 and 2 and minus 2. So it has 3 roots there. So the Galois group is D2 here, but of course we know that already because the splitting field is Ki. Okay, so this is just revisiting a well-known example with something that we already know. Okay, so now the third example I want to do. So maybe I'll just, yeah, so I don't want to use ABC because I'll use them later. So this one is x power 4 minus 4x square plus 2. So I want to do this also explicitly without using any formulas for resolvent cubic. So here you check that roots are plus minus 2 plus minus square root 2. Okay. So here in fact what you can do is, if you take x equal to 2 plus root 2 square root and you compute the irreducible polynomial, you get x square equals 2 plus root 2 and then do x square minus 2 equals root 2. So that means square again. So that will be x square minus 2 whole square equals 2. So this is x power 4 minus 4x square plus 4 minus 2. So that is plus 2 equal to 0. So the irreducible polynomial of this is this, and this is of course irreducible by Eisenstein. And we know that earlier two polynomials are also irreducible. One can check that. I mean, I'll leave that for you. And this is irreducible, and the other roots are given by this. Of course, you can take minus of this. It will have the same irreducible polynomial, but you can put minus here also. So the splitting field is actually, okay. So this is an exercise again. Okay, so the 4 roots are negative of this is already there, but all you need to do is to show that square root 2 minus root 2 can be expressed as a polynomial of this. So and that I can, I'll tell you what it is and you can check this. Okay, so this is again in K, because once square root 2 plus root 2 is there, right? So square root 2 plus root 2 is in K. It means 2 plus root 2 is in K because you can square this, but 2 is of course in K, so root 2 is in K. That means root 2 divided by, and then you simply check that these are equal. This ratio is this. Okay, this is a triviality. So here Galois group has order 4, right? Galois group has order 4 because K over Q is degree 4. You attach one of the roots, other roots are already there, and that root has degree 4. So, and in our list, what are the degree 4 things? It's either D2, which has degree 4, D4 has degree 8, A4 has degree 12, S4 has order 24. So it's either D2 or C4, but which is it? So I claim that you can check this by computing the resolvent cubic and showing that it will have exactly one root and not all 3 roots in Q. But more directly one can check that G contains an order 4 element. What separates the Klein 4 group and the cyclic group of order 4? Klein 4 group has all elements of order 2 other than the identity. C4 has an element of order 4. So if G contains an element of order 4, one can show that, then it will follow that it is C4. So let us consider this particular, so sigma of square root, so to determine automorphism of K, all you need to say is what is the image of the generator, which is square root of 2 plus root 2. I will define this to be, it can be any of the 3 other conjugates, any of the 4 conjugates. So I will take 2 minus root 2 square root. Okay. So then check that sigma square of this is actually sigma of this, which is square root 2 minus root 2. So again I am going fast about this, and using the fact that square root 2 minus root 2 is root 2 divided by sigma of square root 2 plus root 2, and then you do a little bit of analysis and show that. Okay, so this is an exercise. So as I said, I want to do as many problems as possible. So I do not want to do every detail. So I want to isolate where I leave the exercise for you. So this equality is an exercise. It's a trivial exercise, computational exercise. So that means sigma square is not identity, right? So this is not square root 2 plus root 2. So this means G cannot be D2, because in D2 every element has square equal to identity. So G is C4. Okay. So you have an example with C4, you have an example with D2, and you have an example with D4. And for other things, I want to introduce now some more theory and some general useful facts about discriminants and resolvent cubics. And this is the following. So if you have a quartic polynomial of the form x power 4 plus cx plus d, okay, so it has no cubic or quadratic term, then it just happens to be 256 d cubed minus 27 c power 4, okay, and the resolvent cubic of the same polynomial. Okay, so these are some computational things which one can find in literature. You can take help from some notes, online notes that you will find, and compute this. And so I don't want to get into that computation. I would rather use just these formulas to give you some interesting examples. Okay, so these are facts. Okay, so you can find them in literature. Just search for this. If you have any questions about where to find them, please feel free to contact me or ask in discussion forums. Okay, so now using this, I want to consider this polynomial, okay, as a rational polynomial. And again, I want to quickly move on to the next problem. So I will let you check this. F is irreducible. Check by going modulo 2. So go modulo 2 and show that that polynomial is irreducible. It's not enough to show that it has no roots, right? Because it's degree 4. First you have to show it has no roots, then it can split potentially as a degree 2 times degree 2. You show that that's not the case modulo 2. So this is an exercise for you. So this is an irreducible polynomial of this form. So the discriminant you can compute using this formula here happens to be minus 283. So this is not a square because it's a negative number. So it's not a square, and G happens to be x cubed plus 4x minus 1. Okay. So this also you can check is irreducible. I will let you check this by, for example, rational root test. Here any root must be 1 or minus 1, but neither of those is a root. So there are no roots, it's a cubic polynomial, so it is irreducible. So we have G irreducible and D not a square, so it must be S4. So Galois group of F is S4. Okay, so this I'm trying to give you examples of every group here. D2 is covered, D4, C4 are covered, S4 is covered. Now let's look at an example with A4. And this also I will sort of not explain in detail. You take this. I claim, you cannot apply Eisenstein, and it's not clear, it's not immediate. It requires some work to do this. First show that F has no roots using rational root test. Show that it has no roots, that one can check, because any root must be an integer that divides 12, and you check for all of those divisors of 12, none of them is a root, so it has no rational roots. But that doesn't immediately imply, unlike in the degree 2 or 3 case, that this is irreducible, because there is a chance that it can split as an irreducible quadratic times another irreducible quadratic. Now show that f mod 5 is a linear polynomial times a cubic irreducible polynomial. Okay, so a linear polynomial times a cubic irreducible polynomial, and you show that if f as gh, g and h are degree 2 irreducible, then if you have this implies that f has 2 roots modulo 5, but this violates this. Okay, so f has exactly 1 root modulo 5. So you can show this, all this using these exercises. So this is not easy. So this is an exercise, but one can do this. This is a good exercise to get experience with computing irreducible, verifying irreducibility of polynomials, but I don't want to get into that. So this is irreducible, and just applying blindly this formula, you conclude that discriminant is actually 3 square 2 power 6 square. So t is a square. Okay, so just blindly apply this and you get the formula is here. You apply the formula for discriminant, you get this, and g happens to be x cubed minus 48x minus 64, and you can check that this is irreducible by going modulo, for example, 5. So you can either do rational root test or directly check modulo 5, and you look at it and you show that it has no root, so it is irreducible modulo 5. So this is irreducible in Q itself. So we are in this situation where discriminant is a square but G is irreducible, and hence Galois group of F is A4. Okay, so you have all possibilities now, right, that we have covered. So you have A4, S4, D2, D4, C4. So all the 5 examples are covered now. Okay, so now let me just do one more simple thing to just illustrate what happens if you have higher degree. Okay, so let's see. So I want to find where I wrote this. So degree 5 we have considered earlier, and so last thing I'll do 5, 4, vertex is 3, so 4. So I give you a polynomial of degree 6 like this. So x power 6 minus 2x5 minus x4. I hope I have done this calculation correctly. So, but you will see this is a trick question. So what is the Galois group of this? Of course, it looks very strange, and you have no way of doing this, right, for degree 6. But I cooked it up exactly so that you have x cube minus 2 times x minus 1 times x plus 1 times x minus 2. So 1, minus 1, 2 are all roots of this. Okay, so now these are all going to be linear in Q, and this is irreducible. So Galois group of F is actually nothing but S3, because x cube minus 2 has S3 as the Galois group. Okay, I just wanted to do this to illustrate that just because you have large degree doesn't mean that Galois group will be, it's also a big group. It could, depending on the factorization of the polynomial, you can fall back into smaller essence. Okay, so now let me do one more problem. So before I stop this video, so I lost track. So the second problem was computing Galois groups. So third problem, still with quartics. So let's say F is an irreducible quartic degree 4 in other words, which has exactly 2 roots, real roots. So then I claim that, show that the Galois group of F is either S4 or D4. It can't be others in the list that we have. So why is this? So let us prove this. So let's say K is the splitting field of F. Then what we have is, and so let's say alpha is a real root of F. So then we have Q alpha and Q. So this is of course 4 because F is irreducible, right? So this is 4 and Q alpha is not equal to K because K is not contained in R. Because it has exactly 2 real roots, means the other 2 roots are complex and not real. So K must not be contained in R, but Q alpha is contained in R. So this cannot be 1, so it's at least 2. That means K colon Q is at least 8. That means the Galois group order is at least 8. So now in our list there are not too many with order at least 8 because other things are D2 and C4, they are order 2 and order 4. So these are the only possibilities. Now which of them can it happen? So the question is asking it's either S4 or D4. So we have to rule out A4. How do we rule out A4? We rule out A4 by, remember A4 happens when discriminant is a square. This happens when discriminant is not a square. So now I claim that discriminant of F is negative. Then it cannot be a square. And this is an easy statement. So let's say the roots are alpha 1, alpha 2, Z and Z bar are roots of F with alpha 1, alpha 2 in R and Z not in R. Okay. So then what is the discriminant? I mean, I'll just go and directly compute the discriminant. I have an arbitrary quartic, so I can't use the formula that I wrote earlier. So this is simply, remember discriminant is alpha I minus alpha j whole square for all I less than j. So this is alpha 1 minus alpha 2 square. So I'm just going to write all of them. Alpha 1 minus a minus ib. So z is a plus ib, let's say. So z bar is a minus ib. So of course b is non-zero because z is not in R. So z minus a minus ib, alpha 1 minus that, alpha 1 minus z bar will be minus a plus ib, and then I'll write z alpha 2 minus a minus ib, alpha 2 minus a plus ib. You see where this is going. And finally z minus z bar. What is z minus z bar? A plus ib minus a plus ib. So this is 2ib. So 2ib whole square. Okay. So now let's look at individually what the sign of these things are. So this is of course positive. They are all distinct roots, right? So this is positive and this is negative. That is because that's b is positive, b is non-zero, so this is minus 4b square, so that is negative. And together this is alpha 1 minus a whole square plus b square, so this is positive, this is positive. So the discriminant is negative. And hence the Galois group cannot be, so that means discriminant is not a square. So this implies Galois group cannot be contained in the alternating group. So this is ruled out. So this implies, and for order reasons, D2 and D2 of course is ruled out because discriminant is not a square, but C4 is ruled out for order reasons, and as required it is S4 or D4. In fact, both of these occur. And I leave this as an exercise for you. I don't intend to do this, but a similar calculation will tell you that if F is a irreducible quartic, so exactly as before, so I don't want to call it a new name. So irreducible quartic, so this exercise, f has 0 real roots. So of course it has 4 roots. If all of them are non-real, then discriminant of f is positive. If f has 4 real roots, also the discriminant is positive. And if f has exactly 2 real roots, exactly of course everywhere, then discriminant, this we have done, right? So this is the above problem. Okay, so in general the discriminant will tell you what happens with respect to the discriminant of the number of non-real roots will tell you the sign of the discriminant. Discriminant is of course a rational number, so whether it's positive or not, and it's a non-zero number because your irreducible polynomial, so distinct roots, so discriminant is certainly non-zero. Okay, so let me do 1 or 2 more problems before I end this class. So just to settle, these are problems that I touched upon in the videos, the earlier parts of the class. So okay, let f be, as always I'll stick to the complex subfields of complex numbers. Let f be a polynomial of degree n. Then the problem is asking you to show f is irreducible if and only if Galois group of f is a transitive subgroup of Sn. We certainly know that Galois group is a subgroup of Sn, but it is a transitive subgroup if and only if f is irreducible. Okay, so this I needed this statement in the proofs of solvability of polynomials, but I wanted to record this explicitly so that you have this in your notes. So I don't want to spend too much time proving this because we have essentially proved this. If alpha and beta are 2 roots of K, of course, is a splitting field, then f irreducible implies there is a function from f alpha to f beta, f isomorphism sending alpha to beta. Extend this to get sigma from K to K, sigma in Galois group of Kf, which is of course the Galois group of f, sending alpha to beta. Okay, so G is transitive. So for any 2 roots, there is a Galois group element which sends one to the other. So it is transitive. Suppose it is f is not irreducible, or in other words f is reducible, then f can be written as G times H, where degree G is positive and degree H is positive. Okay, but now any element sigma of G must permute roots of G and permute roots of H separately. What I mean is, any root of G has irreducible polynomial which is a divisor of G. So, and that cannot be a root of H. We can assume that G and H are co-prime. Okay, so what I want to say is that there must be a root of G that's not a root of H. There must be a root of H that's not a root of G. So no element sigma of G can map a root of, okay, so actually there is a little bit more work involved here, so I'll simply say that. So using this decomposition, this is a true statement. Using this factorization, conclude that G is not transitive. So there is a root that you cannot permute. Okay, so the point is it must be a transitive subgroup of Sn. N is important, and where n is the degree. It cannot be a transitive. It can be a transitive subgroup of a smaller symmetric group Sn minus 1, and F can fail to be irreducible. But if it is a transitive subgroup of Sn, there must be a root of H that cannot be mapped to a root of G. Okay, so this last part is the exercise. Again, I am not doing everything possible, so that I am covering as many exercises as possible. So let's do just one more problem before we end this class. This is also something we have done before. Now let's take F to be an irreducible polynomial. As always, capital F is a subfield of C. Then if a root of, if one root of F is solvable, then all roots of F are solvable. Then F itself is solvable. Solvable over F, of course. Then all F is solvable, that means all roots of F are solvable. And the proof is fairly clear. So suppose alpha in C is a solvable root of F. Okay, so you have a tower starting with F and ending with a field. This is simply radical, simply radical, simply radical, and alpha is here. But now using a theorem that we proved about extending a radical extension to a Galois extension. Given a radical extension, you can enlarge the field to get a Galois extension which is radical. So you can extend to some K or L such that this is radical plus Galois. But now L over F is Galois implies L over F is normal, and F is irreducible and has a root. So alpha is of course in Fr, so alpha is in L, has a root alpha in L. So F splits completely in, right? So that means all roots of F are solvable, right? Because all roots of L are in a radical extension. So every root is solvable, hence F itself is solvable. Okay, so let me end this class now. We have done several problems on computing Galois groups and some observations that we have made during lectures. I wanted to formally record them here. So let me stop now. I will continue with more problems in the next class. Thank you.